Hi friends, welcome to Cracku's online classes. I'm Saili Kale. I'm one of the co-founders of Cracku and an alumna of IIM Ahmedabad. In today's class, we'll be covering the second half of our quant revision. So in our first quant revision video, we covered geometry and arithmetic topics such as time, speed, distance, profit and loss, time and work, etc. So in today's class, we'll be covering the remaining quantitative topics. So let's get started. So we'll start off with the biggest part of this, that is number systems. So let's begin by first reviewing the basics of number systems. So number systems, the questions that generally come are how many such numbers exist, or what would be the remainder when x is divided by y, or how many numbers can be formed such that they are divisible by x, or something like that. So let's first define what a divisor is, what a quotient is, what a remainder, etc. is. So suppose a number n is written as a into b plus c. Here so a would be the largest multiple of b that is less than or equal to n. So here n is the number, b is the divisor. Here a is called the quotient and c is the remainder. So what does the remainder mean? So remainder is the part that is left over. So suppose you have a number, say 17, and you divide it by 4. So what is the largest multiple of 4 that is less than or equal to 17? The largest multiple of 4 that is less than or equal to 17 is 16. And the part that is left over after removing the largest multiple is called a remainder. In this case, after removing the largest multiple, the part that is left over is 17 minus 16, that is 1. So the remainder when 17 is divided by 4 is 1. The quotient is the multiple of 4 which is less than or equal to the given number. So in this case 4 into 4 is less than or equal to 17. So the quotient in this case would be 4. So essentially in this whenever we are given a number and a divisor, we can express the number as n into a. Here a is the quotient, b is the divisor and c is the remainder. In this case c will be less than or greater than or equal to 0 and less than b. So when the remainder is 0, that means that the number is perfectly divisible by the divisor, and it should be less than b means that if it is equal to b, it means you could have added one more to the quotient and made a perfectly divisible number. So the number varies essentially from 0 to b minus 1 as such. We can write remainders in two ways. We can either write the remainder in a positive way or in a negative way. So suppose we took the case of 17 divided by 4. Now in this case the remainder can be written as 1, or you can also write it as 4 minus of 4 minus 1. So you can also write it as minus 3. So you can choose to write it in either way depending on what is convenient to you. So the reason for this is that suppose you have a large number where so suppose like you have just one less than the number that is divided. So for example, if you have instead of 117 you have 116 when divided by 13. Now 117 is a perfect multiple, but 116 is just one less than that. So either you could write the remainder as you can write this as either 12 or you can write this as minus 1. And the benefit of writing it as minus 1 is the fact that it is easier to express, like if you have minus 1 as the remainder, you can multiply it across other remainders and it will generally tend to cancel off the minus sign, so it will become easier to cancel off 1. I will go into the basic properties of remainders later on, but just remember that whenever you have a remainder of this form, you can write a remainder in a positive way, that is like 12, that is the amount left behind, or you can write how much is deficient to form the next highest coefficient as such. So that is how you can write remainders. Now the basic properties, you have to remember two basic properties of remainders. First is the addition rule. So the addition rule basically says that if you have for like shorthand, we'll instead of saying remainder of a divided by b, instead of saying all of that, we use the modulus operand. So to say that what is the remainder left when a is divided by b, we just write it as a mod b. This gives you what is the remainder left when a is divided by b. So what is the so all functions are defined for this modulus operator as such. For sometimes I can also use this kind of operand for defining modulus, but generally I would write down the entire this so as to avoid any kind of confusion with the percentage symbol as such. So A mod B refers to the remainder that is left when A is divided by B. So what is the addition rule? The addition rule says that when two numbers, one more than say 2, 3, 4, whatever numbers are added together and you divide it by some divisor, say n, you can split this in such a way that where you put this mod operator inside the sum as such. So you can write this as A mod n plus B mod n plus C mod n plus D mod n, the whole mod n. Now why is it important to write the whole mod n outside? So imagine the case when like say A, B, C and D are just one above the n. So suppose this is like n plus 1, this is 2n plus 1, this is 3n plus 1, this is 4n plus 1. In that case, what would be the remainder when all of, suppose it's like n is say 4 and this is of the form say, take the example of 5 plus 9 plus 13 and 17, mod 4. Now if I take mod 4 inside, I get 1 plus 1 plus 1 plus 1. Now the remainder, and if I don't take the mod 4 again outside, the remainder it will tell me the remainder is 4. But this is because I'm adding up all together. Now after adding up all together, I will get a number which might be equal to or greater than 4. So to get the actual value of the remainder, I have to again say mod 4. And then I will get the actual remainder, that is 0. So whenever you, after putting the modulus operator inside the sum, you have to again take mod n just to make sure that the end remainder that you get makes sense and is less than n as such. So that is the first rule, that is the addition rule. The second rule is multiplication rule. The multiplication rule says that if you have the multiple of say here I am taking 4 numbers, but it's true for n numbers. There is no such this as such. So if you have a multiplication like this, you can take the modulus operator inside. So you can say that this is equal to A mod n into B mod n into C mod n and so on, D mod n, the whole mod n. You have to take again mod n outside. So this is how you can split up, if you have a complicated remainder theorems question, you can split it up into easier to calculate subparts and then multiply them back together. Another place where you often use this is, suppose you have a this of the form where like suppose it is what is the remainder when say p times a raised to n is divided by pq. Here pq is a say q is a prime number. So what you can say is that I'll cancel p from the numerator and denominator, but the fact is that when you have p raised to n divided by pq, the remainder that you also get, you should also multiply that with p. The reason for this is that you are expressing this in this form where n is equal to a into b plus c as such. So if you have n is as pa raised to n plus is equal to a times pq plus c, and you have to find c. So whenever you are like saying, okay, I'll cancel off p from both numerator and denominator, you are implicitly in that case dividing the remainder also by p. So whenever you are doing this, you can do that. So first step is you cancel off the common factor from numerator and denominator, find out the remainder, but make sure that you multiply that remainder with p to find the actual remainder. Many people skip this step or miss this step. So always remember that when you are cancelling a factor from numerator and denominator in remainder theorem questions, after calculating that remainder, you are supposed to multiply back that common factor. So that is the second thing. The last thing that you have to remember over here is what I had mentioned about positive and negative remainders. So why is this important? So suppose like if you had a remainder of this form where you had like say all of these were n minus 1 mod n. So if I could have either written as n minus 1 into n minus 1 into n minus 1 into n minus 1 mod n, and I'll get n minus 1 raised to 4 mod n, but that would have been difficult for me to calculate. Instead of that, if I write minus 1 into minus 1 into minus 1 into minus 1 mod n, I get essentially 1 mod n and that value will be 1. So that is how you should think of it. if you put it as a negative remainder and you are going to use the product multiplication rule, your negative remainder of like negative -1, negative -2 is much easier for you to handle than a bigger number like 12 or 13. So that's what you should keep in mind while using the negative remainders. So these are the basic tenets on which the most of the number system questions are based. Now let's take a look at the basic divisibility rules. So though remainder theorem questions come in CAT, most often we see simpler questions in CAT, that is how many such numbers are possible such that they are divisible by 2 and 3, divisible by 4 and 5. So here you need basic divisibility rules and basic ideas about what is the remainder, what is the how many numbers are divisible, etc. So let's first write down the divisibility rules. So first is divisibility by 2. Most of you would know this, divisibility by 2. So every even number is divisible by 2. So anything that ends with 0, 2, 4, 6 or 8 is divisible by 2. When it comes to 4, the last 2 digits should be divisible by 2. So if the number is so the number is say 1396, you just consider the last 4 digits. The last 4 digits are 96. They are divisible by it is divisible by 4, so 1396 is divisible by 4. In the case of 8, you have to consider the last 3 digits. The last 3 digits should be divisible by 4. So here, sorry, in the case of 4, the last 2 digits should be divisible by 4. In the case of 8, the last 3 digits should be divisible by 8. Okay, sorry. So for example, if you have a entry of the form say 13,008, in that case the last 3 digits are 008, which is divisible by 8. So the number would be divisible by 8. And same with 16. In this case there are last 4 digits and that should be divisible by 16. So this is the same simple rule that you have to follow. This is the simple rule to check whether or not a number is divisible by powers of 2. Now for powers of 3, so for to check whether a number is divisible by 3, the sum of the digits should be divisible by 3. This most of you would know already. In case of 9, the sum of digits should be divisible by 9. So sum of digits should be divisible by 9. For 27, instead of taking the sum of digits, you have to take sum of blocks of 3 taken from right to left. So suppose the number is 1, 2, 3, 4, 5, 6, 7, 8, 9 and 0. Then the blocks of 3 are 890, 5, 6, 7, 1, 2, 3, 4 and then last is 1. So you have to take 1 plus 234 plus 567 plus 890, sum of these, and that should be divisible by 27 for the entire number to be divisible by 27. So sum of blocks of 3 right to left and divisible by 27. So this is the basic this for powers of 2 and powers of 3 as such. Now we'll come to checks for so let's say next is divisibility by 5. For a number to be divisible by 5, it should end in 0 or 5. For a number to be divisible by 6, it should be divisible by both 2 and 3. For the divisibility of 7, it really doesn't make much sense to use that because it reduces the number of digits one at a time. So for a given large number, it doesn't make any sense whatsoever. So I'm going to skip that. The last divisibility test essentially that you need to remember is divisibility by 11. In this case, the sum of odd digits minus sum of even digits this difference should be divisible by 11. The thing with all of this is that essentially now with the calculator you don't have to check whether a number is actually divisible by another number. What you have to do now is that given this information you have to now frame what are the possible cases when numbers will be divisible by another number. So here I am saying that sum of odd digits should be minus sum of even digits should be divisible by 11. Now this puts restrictions on what kind of digits will be there in the odd places if say digits in the even place are already decided, or suppose you are given like n minus 1 digits and you are supposed to pick the nth digit, then there are restrictions on what the nth digit would be if it is given that the number is divisible by 3 or if the number is divisible by 11. So all of these restrictions would be there if some of the digits are already chosen for you. So these rules are not necessary for you to actually just divide a by b, but for you to define like general forms that numbers can take given that they are divisible by 3 or divisible by 11 as such. So this is what you should remember while solving questions which ask you that how many such numbers would be divisible by 6, or how many numbers that begin with the number 4 or 5 will be divisible by say 55. Then you have to remember that okay, it has to be then be divisible by 5 and therefore it has to end in 0 or 5, and then it has to be divisible by 11. So sum of odd digits should be sum of odd digits minus sum of even digits should be divisible by 11. So from that you get an expression or an equation, and using that you can count a number of possible cases where that rule is satisfied as such. So these are the basic divisibility rules. Let's go on to the concept of factors. So basic thing with number systems is that you should first have a good hold on what factors are. So any number n can be represented as a product of prime factors. So say suppose the prime factors are p, q, r, and essentially the number will be represented as this prime factor raised to a, this prime factor raised to b, this prime factor raised to c, and so on. So for example, if you consider 60, so 60 is a multiple of, if you prime factorize it, let's see how many these are there. So it is a multiple of 2, it is a multiple of 3, and it is a multiple of 5. So these are the 3 prime factors in 60. Now let's consider what is the highest index of 2, 3 and 5 in each of these. So we have 2, this is divisible by 4, so 2 raised to 2 into this is not divisible by 9 or anything, so the highest index of 3 is 1. Similarly, it is not divisible by 25, so highest index of 5 is 1. So 60 can be represented as 2 square into 3 into 5. So this is how you prime factorize numbers. So essentially, if you represent a number as a multiple of its prime factors, like p raised to a into q raised to b into r raised to c, etc. Here a is the highest index of p in n, b is the highest index of q into n, and c is the highest index of r in n. So this will be divisible by r raised to c, this will be divisible by r raised to c minus 1, and so on. So the number of factors of n would be 1, p square, p cube, and so on till p raised to a. Then we will have q square, and so on till q raised to b. Then you will have r square, and so on till r raised to c. So these are the number of factors. To calculate the total number of factors, you can see that this is essentially like a GP. So because this is a GP, you can calculate this as the number of factors by considering how many terms would be there in the GP. So in this case, the number of terms that would be there in the GP would be, so the number of factors, if the number is p raised to a into q raised to b into r raised to c, so the number of factors in this case would be a into 1 into b in plus 1 into c plus 1, c plus 1, and so on. So why is this the number of factors? Because so essentially for if you think of it, each of these numbers, so this is the when you take each of them individually. Then you can also have the cases where you have p raised to 1, q raised to 1, and so on. So essentially you can choose p from p raised to 0 to p raised to a. You can choose q from the range of q raised to 0 to q raised to b, and you can choose r from r raised to 0 to r raised to c. So essentially you have 1 plus A choices. Here you have 1 plus B choices, and here you have 1 plus C choices. So essentially you can the total number of factors would be one of these values for P into one of these values for Q into one of these values for R. So the total number of factors would be 1 plus A into 1 plus B into 1 plus C. So this is how we get the concept of total number of factors. Now if you are asked how many factors would be there such that the number of factors which have at least P square in it. Now if you have to consider that at least P square will be there, in that case this range does not go from 0 to A. This range then goes from P raised to 2 to A. So the total P raised to A. So the total number of factors would be, this is A, so this is A minus 2. So the A minus 2 plus 1, so A minus 1 factors will be there. So in this case, you take A minus 1 into 1 plus B into 1 plus C. So this is how you should remember how the number of factors have come. So if you are given that how many factors this number has such that they are also multiples of A square into B square. So you have to then say, okay, now my range for the prime factors is not P raised to 0 to P raised to A, it is now P squared to PA. It is Q squared to QB, etc. So then you have to choose your range accordingly. Once you have the range, then you can calculate how much of that is applicable for you, and then product of that will give you the total number of factors. So why am I discussing this? So the common condition that comes is basically how many are even factors or how many are odd factors. So generally let's say that one of the factors, say here in this case, let's say P represents 2, the highest power of 2 in N. So say N is of the form 2 raised to A into Q raised to B into R raised to C and so on. So in this case, if I have to consider only even factors of even factors of N, in that case I am saying that I must have at least 1 2 in it. So if I must have 1 2 in it, then this range for me is 2 raised to, earlier it would have been 2 raised to 0 to 2 raised to A. This would have been Q raised to 0 to Q raised to A, Q raised to B, and R raised to 0 to R raised to C. But if I say that I must have only even factors, then this range is just 2 raised to 1 to 2 raised to A. Then I have not 1 plus A factors, but I have A choices. Here I have B plus 1 choices, here I have C plus 1 choices. So the total number of even factors is A into B plus 1 into C plus 1 and so on. Now obviously the number of odd factors would be total number of factors minus this. So total number of factors minus this would be 1 into B plus 1 into C plus 1 and so on. There basically I am saying that the only power of 2 that I can take is 2 raised to 0. I can't take any other power of 2, and I can take any power of the remaining prime factors as such. So this is the number of odd factors and number of even factors. So this is basically the concept behind prime factorization: number of factors, number of even factors and number of odd factors. So whenever you see how many such factors are there such that they are also multiples of A square and B square, first write down the prime factors, find out the prime factors ranges, that is, it will be, the range will go from 0 to the highest index. Then say, okay, no, it won't go from 0 to higher index because I have to also satisfy these particular conditions. Then write down the real ranges given these conditions, and then multiply those the number of values in each of those ranges, and product of that will give you the total number of factors that satisfy the given condition. So this is about factors. Now let's come to the main this of remainder theorems. So so I have like a basic step-by-step tree that one should follow while calculating remainder theorems questions. The first thing is that if the numerator is easy and both of them are like single digit numbers, like suppose you have 3 raised to 203 divided by 7. If both of these are single digit numbers, then use first thing that you can try to use is the concept of cyclicity. In this case, 7 is a prime number, so it would make more sense to use Fermat's theorem. But suppose it was not like this, suppose this was 8. in this case it's difficult to directly use Fermat's theorem. So in that case, if the prime number, if the numbers both in numerator and denominator are single digit numbers, numerator will obviously be single digit raised to some index, denominator is a single digit number, then use the concept of cyclicity of remainders. So what is the concept of cyclicity of remainders? The thing is that when you have remainders theorem, remainder kind of questions, the remainders tend to kind of follow a pattern. So like suppose 3, like if I take the example of 3 and 8, 3 raised to 1 mod 8 is 3. 3 raised to 2 mod 8 is 9 mod 8, that is 1. Then 3 raised to 3 mod 8 is 27 mod 8, that is again 3. 3 raised to 4 mod 8 is 81 mod 8, that is again 1. So essentially even powers of 3 mod 8 gives you 1 and odd powers of 3 mod 8 gives you 3. So just by using the cyclicity of factors, I can say that 3 raised to 203 mod 8 will give me the remainder as, so 3 raised to 203 mod 8 will be 3, because odd powers of 3 raised to odd powers of odd powers mod 8 gives me 3 and 3 raised to even powers mod 8 gives me 1. So basic concept you should use in if the denominator is a single digit, the numerator is a single digit, try to first think of the concept of cyclicity of factors. Now the second concept that you can use is Fermat's theorem. So in Fermat's theorem it basically says that according to Fermat's theorem, a raised to p minus 1 mod p, so suppose a raised to p minus 1 mod p is equal to 1. Here p is a prime number and a and p are co-prime to each other. So what does co-prime mean? That is a is not a multiple of p essentially, and there is no common multiple between them. So for example, 28 and 5 are co-prime to each other. It doesn't mean that 28 has to be a prime number. You can even say 28 and say 15 are co-prime to each other, because this is not a prime number, this is not a prime number, but this is essentially 4 into 7, 2 raised to 2 into 7, and this is 3 into 5. So they have no prime factors in common. So whenever two numbers have no prime factors in common, they are co-prime to each other. So for Fermat's theorem to be applicable, the denominator should be a prime number and the numerator, the numerator will be raised to an index. So a raised to p minus 1 mod p. Here a and p should be co-prime to each other. So this is the basic condition. So what does this mean? So for example, if I had this 300 raised to 203 mod 7, now I have 7 is a prime number. So I can use and 3 and 7 are co-prime to each other. So on the basis of this fact, I can use Fermat's theorem here. So what would I say? This would be 3 raised to, this means that by Fermat's theorem, 3 raised to 7 minus 1, that is 3 raised to 6 mod 7 is equal to 1. Now what I have to do is I have to find 3 raised to 203 mod 7. So I know that 3 raised to 6 mod 7 is 1. So by using this concept, I will first divide 203 into parts of 6. So what is 203 into parts of 6? I get essentially the last number, that is if I remove 203, that is 2 and 23, so that is 5. So I can represent this as 3 raised to 33 and this raised to 6 mod 7 into 3 raised to 5 mod 7, the whole mod 7. So what have I done here? So basically I have said that I am splitting 203 into a part of 6, that is 198, and the remaining part after removing 198 I have 5. So this part is a multiple of 6. So I take the highest multiple of 6 out of the index. I'll keep it in a separate part. The reason why I do this is because I can say that 3 raised to 33 into 6 mod 7. So because I know that I can change the indices. So this is 3 raised to 6 into 33 mod 7. I take 33 outside. So essentially I say that this is 3 raised to 6 mod 7 into 3 raised to 6 mod 7 33 times. So each of these would be essentially 1 33 times. So I have this, I can convert this into 1. So any part, like first I have 3 raised to 6 mod 7 is 1. So I then take the highest index of 6 out of the overall index that that number has been raised to. I say that is 1. So I remove all of that part and whatever is remainder is left. So I have 1 raised to 33 into 3 raised to 5 mod 7, the whole mod 7. So this I have, because it is 3 raised to 5 mod 7, this is essentially 243 mod 7. Again 243 mod 7 into 1, so essentially I have 243 mod 7 as the final this. So I can just use divisibility over here and have this is 333, so I have 5. So this I get as 5. So essentially I have converted that 3 raised to 203 mod 7. I removed all the parts where I could get where 3 raised to 6 mod 7, wherever I could remove that part, I removed it into a separate section. Using the multiplication formula, I said that okay, there are 33 such parts like this, I make all of them 1. So they are, I'll just have 1 into 1 into 1 into 1, so that's just basically 1. That into 3 raised to 5 mod 7, the whole mod 7. So in the end, I'm left with 3 raised to 5 mod 7. So 3 raised to 5 mod 7, I can just multiply. 3 raised to 4 is 81 into 3 is 243. 243 mod 7 is 5. So this is a basic funda behind remainder theorems with Fermat theorem. Now, in case you don't have a prime number in the this, but the a and p are, suppose instead of p you have some number n, and suppose it is a raised to x divided by n. Now n is not a prime number, but a and n are say co-prime to each other. So what do you do? In case a and n are co-prime to each other, what you do is you find Euler's totient value of n. So what is Euler's totient value of n? So if n can be represented as p raised to a into q raised to b into r raised to c, that is these are the prime factors of n. If n can be represented as the product of prime factors like this, then phi of n, that is the Euler's totient value, function value of n, is n times 1 minus 1 by p into 1 minus 1 by q into 1 minus 1 by r and so on. So for example, if I have the this as say the function, so suppose the value that I have to find out is say 3 raised to 203 divided by 25. Now this is not a prime number, but these two are co-prime to each other. 3 and 25 do not have any factor in common. So then I can use Euler's function as such. 25 I can write as phi square, because it is phi square. 5 of 25 will be 25 into 1 minus 1 by 5. So 1 minus 1 by 5 is 4 by 5. So this is equal to 20. So essentially what I will say is phi of the Euler's totient function value of 25 is 20. Now I have found the Euler's totient function. So according to Euler's theorem, if a raised to x, if you have if you have to find the remainder of a raised to x mod n, and a and n are co-prime to each other, then a raised to phi of n mod n will be equal to 1. Here essentially I am saying that I am first finding out the Euler's totient function value of n. Here a and n are co-prime to each other. I find the Euler's totient function value for n. Then I am saying that a raised to the Euler's totient function value mod n will be 1. So what I am saying from this is 3 raised to the Euler's totient function value for 25 was 20. 3 raised to 20 mod 25 is 1. Now if 3 raised to 20 mod 25 is 1, I can split 200 in 203 as 20 into 10 plus 3. For the 20 into 10 part, I will put as multiplication of 10 parts, each of whose product is 1. So 3 raised to 20 mod 25 into 3 raised to 20 mod 25 10 times. That is 1 into 1 into 1 into 1. So all this part disappears. In the end, I will just be left with so 3 raised to 203 mod 25 essentially becomes 3 raised to 3 mod 25, because the 3 raised to 200 mod 25 that remainder is 1. So 3 raised to 3 mod 25 is 27 mod 25, that is 2. So using the Euler's theorem, I could easily calculate 3 raised to 203 mod 25. So these are the three basic theorems that we have covered till now: cyclicity of factors, Fermat's theorem, and Euler's theorem. Again, I will always say that check with in this order: cyclicity of factors order, second is Fermat's theorem if the base is prime number. If the base is not a prime number and the two numbers are co-prime to each other, use Euler's totient function. Now we come to the concept of Wilson's theorem. So when should you think of the Wilson's theorem? So you should think of Wilson's theorem if your numerator has a factorial in it. So basically, what does the Wilson's theorem say? The Wilson's theorem says that if n is a prime number, then n minus 1 factorial mod n is equal to minus 1. So essentially, like you know that minus 1 is another way of representing n minus 1. So you can say that it is n minus 1, or you can say it is minus 1. So for example, 16 factorial mod 17 is equal to minus 1 or 16. So this is how you should think of it. Whenever you see that there is a factorial in the numerator, there is a very high chance that this is based on Wilson's theorem. So the next theorem that we will see is the Chinese remainder theorem. So when should you think of the Chinese remainder theorem? You should think of the Chinese remainder theorem when you can express, suppose the problem is of the form m mod n. Here n is a composite number and n is the form of a into b, where you can split this is a composite number and you can split it up either into two prime factors. Like for example, if the number is 15, then you can say it is 5 into 3, or if it is 27, you can say it is 3 into 7, and so on. So whenever you can clearly see that this is a composite number that is made up of two prime factors, then what you can do is you can find the value of when m is divided by one prime factor and when m is divided by the other prime factor, and then combine those two remainders together to find the combined remainder as such. So that is what Chinese remainder theorem does. It helps you split the denominator into two factors. You have to split them into two co-prime factors. In this case, like you can even have, like instead of say 15, suppose it is like 12, you can even say it is 4 into 3. It need not be prime each time, but these two parts should be co-prime to each other. That is the basic condition. So essentially, whenever you have a composite denominator, you can split it up into two parts like these, find out the remainder in each case, and then combine them together. I'll explain how to combine them together. But first, when should you use this and when should you use Euler's totient function? Even Euler's totient function is applicable when the remainder is a non-prime number. In case of this, you should think of it when you can see that it is clearly the multiple of numbers, or the two co-prime numbers that you can split them into. If you can easily find m mod m mod a and m mod b, then you should think of this, because if you can easily find like the remainders for the subparts, then combining them together becomes easier. If you can't easily find the remainder for the subparts, then it makes more sense to use the Euler's totient function. The thing with Euler's totient function is sometimes for like a lot of composite values, you get large numbers as the totient value function. So you will have like say for example for 25, you had 5 of 25 was 20. So if it was a large enough index, you would remove all multiples of 20. But still between 20 and 25, you would still have a gap of 5. So you would still have, like say if the numerator was 47 or something like that, you would still have 47 raised to 5 left. Or if it was like even a larger number, like say 1 to 1234, you would have 1234 raised to 5. So sometimes you will not be able to cleanly divide in case of Euler's totient function. So both of these are applicable when the number is a composite number, the divisor is a composite number. This is more applicable when you can clearly split it up into prime factors. So always think of this when you can split it up into prime factors, that this might be more applicable. So let's actually see how this is applied. So first thing you do is split it up into prime factors like this. Then you find what is m mod a, that is what is this divided by the first prime not prime factor, two co-prime factors. What is this divided by the first co-prime factor? So suppose this is R1. This is what is this divided by the second part, that is say this is R2. Then you have to write down an equation of the form ax plus by is equal to 1. Like suppose if the factors are 3 and 5. So I have to find x and y such that I can say that 3x plus 5y is equal to 1. So one of these is going to be a positive number, the other is going to be a negative number. So I can say that 5 into 5 is 25, and I can write this 3 into minus 8 is 24. So 3 into minus 8 plus 5 into 5 is 1. So I can write x and y as minus 8 and 5. So that is, x will be minus 8 in this case, y will be 5 in this case. Now what you should do is write a and b like this. You write a as a I'll write here. So a I write here, then I write b over here. Then you write r1, r2, then you write x and y. Then you do this, a into r2 into x plus b into r1 into y. This value a r2x plus b r2y, r1y gives you the remainder when m mod m is divided by n. So for in this case, as we had said, so I'd write 3 over here, I'd write 5 over here, whatever is the r1, whatever is r2 I'll write over here, and in this case I'd found x to be minus 8, in this case I'd found y to be 5. So I'll have 3 into r2 into minus 8 plus 5 into r1 into 5 is the sum of that is essentially the remainder I get while if I by Chinese remainder theorem. Always remember to do again mod n, because the value you might get after this might actually be greater than n. So you'll have to do mod n again to make sure that the value you get is within the range as such. So this is basically the funda between in Chinese remainder theorem. Always remember you have to split it up into two coprime factors, find the remainder for each of the coprime factors, find an equation where x and y are such integers such that this equation is satisfied, ax plus by is equal to 1. Then write it in this way where you just say a r1x, b r2y and draw these two arrows like this, and once you have that, a r2x plus b r1y mod n is the remainder left when m is divided by n. So this is Chinese remainder theorem. There are two other factors, other things that you should remember while in remainder theorems. Suppose you are given an equation or an expression with x raised to something and y raised to something. Remember that x raised to n minus y raised to n is divisible by x minus y. If it is always divisible by x minus y irrespective of whether n is even or n is odd, and x raised to n plus y raised to n is divisible by x plus y if n is odd. So these are the two factors, these that you should remember. So if you have like x raised to 14 minus y raised to 14, you can say that one of the factors would be x minus y. If you have x cube plus y cube, you can say that one of the factors would be x plus y. Whenever you have x raised to n plus y raised to n, if n is odd, then x plus y is a factor. Whenever you have x raised to n minus y raised to n, then x minus y is a factor irrespective of whether n is odd or even. So that is the basic thing you should remember whenever you have an expression in x and y and you are asked which of these could be a possible factor as such. Let's move on to the concept of linear equations. This is kind of a fundamental concept where many other problems, then eventually after you form equations, you will end up with this of like a 2-variable linear equation and a 3-variable linear equation that you have to solve and get the answers. So most of you would know how to solve a 2-variable linear equation. Say suppose it is of the form ax plus by is equal to c and mx plus ny is equal to q. So essentially try to in some way multiply this by say n, this by b, so that you have nax plus nby is equal to nc and this is mbx bmx plus nby is equal to bq. So if I subtract this is equation 1, say this is equation 2. If I subtract equation 2 from equation 1, I will be cancelling off nby and I will get nax minus bmx is equal to nc minus bq, and then I can calculate what would be the value of x. Similarly, I can then calculate what would be the value of y. Solving linear equations, 2-variable linear equations is like a fundamental concept. You can extend this to like 3-variable linear equations also. So when we have 3-variable linear equations, that is a1x plus b1y plus c1z is equal to d1, and you have a2x plus b2y plus c2z is equal to d2, and a3x plus b3y plus c3z is equal to d3. So essentially you have to change the equations in such a way that you cancel off two variables, and then you can calculate the value of, like, say this. So take the equations two at a time in such a way that you end up with you can cancel off one variable, like these two taken at a time, then these two taken at a time, and you will end up with two sets of linear equations and two variables, and you know how to solve a two variable linear equation. Then you will get the answer for one variable, and you can substitute those values to get the second variable, and then that value to get the last variable. So this is the basic fundamental to solving linear equations. There is in case you're not finding any value for the expression, or you're not able to solve the linear equations. So the general way this is expressed at, so suppose this is the set of three linear equations, okay. In case for this we are defined as there's a determinant defined, which is that is a1, a2, a3, that is the coefficients of this, coefficients of x, coefficients of y, and coefficients of z. And then we are defined dx as replace a1 by the constant value, so d2, d3, and b1, b2, b3, c1, c2, c3, and dy as a1, a2, a3, d1, d2, d3, and c1, c2, c3, and dz as a1, a2, a3. So these are like determinant values. I am writing them as matrices kind of way, but they are determinants. Sorry, so this should be a straight line. This is straight line. And b1, b2, b3, and c instead of c I will have d1, d2, d3. So essentially these are the determinants, 4 determinants associated with a three variable linear equation. So according to, like, the basic conditions for linear equations to have a solution is, if d is not equal to 0, then there will be a unique solution. There will be a unique solution for the linear equation. Now if d is equal to 0, dx is equal to 0, dy is equal to 0, and dz is equal to 0, then there will be infinitely many solutions. So what exactly am I saying here? See, essentially these ax plus by plus cz, a1x plus b1y plus c1z, and a2x plus b2y plus c2z and all. So essentially these are representing lines in a 3D space. So if it is a line in a 3D space, then these lines will intersect each other if they are not parallel to each other, or if they are not coincident to each other. Now if they are if they are parallel to each other, then this determinant will be 0. Now if two lines are parallel to each other, either they will be if they have the same slope or something like that, either they will be coincident or they will be parallel to each other. If they are parallel to each other, then there will be no solution. If they are coincident to each other, they will have infinitely many solutions, because all lines on that point will be a solution which satisfies the given equation. So how do you understand whether or not they are coincident or they are parallel lines? If all 4 equations are 0, that means that they are coincident lines. In that case, there will be infinitely many solutions. If one of them is non-zero, that means that there is either 2 of them are coincident and 1 is not coincident, or all 3 are essentially if one of these dx, dy and dz is not 0 and d is equal to 0, then you can't say that there is a solution. There is a very good likelihood that there is no solution as such. So always remember, if d is not 0, then there is a unique solution. If d is equal to 0, dx is equal to 0, dy is equal to 0, dz is equal to 0, there are infinitely many solutions. So this is infinitely many solutions. If dx is equal to 0, dy is equal to 0, if one of these 3 is not 0, then it can be either no solution or infinitely many solutions. So you don't know. So this is the case where essentially you say that we cannot determine the answer, or there can be a possibility that there is no solution. In this case, there is a unique solution. You can answer. For example, if this comes in data sufficiency, you can say you can answer this question. In either of these cases, when d is equal to 0, you cannot find a unique value for the answer. So this is the basic fundamental behind linear equations. If mostly you will just be given what you need to know is that how to solve linear equations. Sometimes you will find that the linear equation is unsolvable. Then you can think of the determinant part of it and then see whether or not the determinant d is 0 or not. If it is 0, then you won't be able to find a unique solution. So that is the basic fundamental behind linear equations. One more thing that you need to understand is that so you need 3 equations generally for when there are 3 variables. You need 2 equations when there are 2 variables. However, like for example in this case, you can find subparts without if you have 2 equations with 3 variables, you generally cannot find an answer. But if you have 2 equations with 3 variables, sometimes you are able to find out values for subparts. Those are called those are called special equations. So generally if you find something of the, let me just clear up some space so that, so if you see that the linear equation is such that the coefficients are in arithmetic progression, like for example 3a plus 5b plus 7c is equal to 11, and you have 5a plus 7b plus 9c is equal to 13. So even though these are not, so even if you have just 2 equations like this, so generally you need 3 equations if you have 3 variables, you need 3 equations to uniquely determine an answer. But if you have if you have special equations, special linear equations like this, you can identify subparts of the answer. Like for example, in this case, you can find out what is the sum of all, what is a plus b plus c. So you can identify what are subparts like this even in such cases, or you can find out what is b plus 2c. So always be on the lookout for special linear equations, especially in data sufficiency. In special linear equations, if the coefficients are in arithmetic arithmetic progression, then you can combine them in such a way that you can find out certain subparts of this. So if you have 2 equations in 3 variables, there are some ways and those coefficients are in arithmetic progression, you can find the sum of all variables. So these are special linear equations. Do take a look at special linear equations, especially because they have some application in data sufficiency. So this is about linear equations. Let's move on to inequalities. The basic thing that you need to remember in inequality is that, see, if you have an inequality of the form a is greater than b, then you can add a number to both sides. You can subtract a number from both sides, but you cannot multiply a into c and b into c unless you are sure what the sign of c is. Because if c is greater than, if you know that c is greater than 0, then this is true. If c is less than 0, you have to essentially flip the sign. In that case, AC will become less than BC. If c is equal to 0, then the inequality no longer holds. So whenever before you multiply or divide by a number, same is the case with divide. So AC and BC, unless I know the unless I know the sign for c, I cannot tell what would be the inequality sign in this case. So basic fundamental of inequalities is that you cannot multiply or divide by a particular number, like on both sides of an inequality, without knowing the sign of that inequality. So that is the basic property that you have to remember with inequalities. When you are multiplying with a negative number, like suppose you have x is less than y, then minus x will be greater than minus y. So because I am multiplying by a negative minus 1, the sign of inequality flips over. So this is the basic thing that you have to remember. Similarly, if I am dividing the number by a negative number, so suppose it is x less than y and I divide it by a, suppose I divide this number by a, x by a and y by a, and I know a is a negative number, then x by a will be greater than y by a, because once I essentially dividing by minus 1 or multiplying by minus 1 is the same. So whenever you are essentially multiplying minus 1 to both sides, you have to flip the inequality sign. This is a basic thing that you have to remember. So another thing that you have to remember is that so if a and b are a is greater than b, and if you raise them to an index, say C, then if C is positive, say if C is like a positive number, C is greater than 0, then A raised to C will be greater than B raised to C. That is simply because if you are raising it to a positive number, you're keeping it in the numerator of the equation. But if C is a negative number, then A raised to C will be less than B raised to C. Because here now I am putting A in the denominator of the number. This I can write this as A raised to C and A raised to minus C and 1 upon B raised to minus C, and this will be a positive, like this will be a positive index, this will be a positive index, and 1 divided by a higher denominator would be a lower number. So therefore that's why whenever you are raising it to a negative exponent, the inequality sign flips. So these are the basic properties you should remember in inequalities. Let's move on to quadratic equations. So a quadratic equation, the basic form of quadratic equation is ax square plus bx plus c is equal to 0. Here for a quadratic equation is because the highest index of x is 2, it will have 2 roots. So if an equation of the form of like where you have ax raised to n will have n roots, because quadratic equation the highest power of x is 2, it has 2 roots. So that is the basic funda of quadratic equation. The second thing that you need to remember, the most important property that is often tested is that if the equation is of the form ax square plus bx plus c, this is equal to 0, then say alpha and beta are the roots of this equation, then alpha plus beta is equal to minus b by a and alpha beta is equal to c by a. So this is the basic, the sum of the roots is equal to minus b by a and the product of the roots is equal to c by a. This is a basic property on which most of the questions in quadratic equation are asked. The second basic property that you have to remember is about the determinant of quadratic equation. So the basic thing of like how do you find out the roots of the quadratic equation? The formula for finding roots of the quadratic equation are, so alpha beta is equal to minus b plus or minus square root of b square minus 4ac by 2a. So this is the formula for finding out the roots of the equation. Now the nature of the roots depends upon this term, because clearly if this term is a perfect square, this would be a rational number. If this term is negative, this will be a complex number. If this term is 0, then alpha and beta will be equal. So all of this depends on this number. So this part is called the determinant. So d is equal to b square minus 4ac. So this is called a determinant of this. So determinant basically is, if determinant is less than 0, you can say that the roots are complex roots, and complex roots will occur as complex conjugates. What do I mean by complex conjugates? That both will be form of they'll be like a plus ib and a minus ib. Now suppose d is equal to 0, then the roots are equal. Roots are equal and rational. If d is greater than 0, the roots are real. If d is a perfect square, roots are real, rational and unequal. If d is greater than 0 and they are not a perfect square, then we can just say that they are they'll be d is greater than 0, not a perfect square, then they are real, and they'll be complex, they'll be conjugate surds. So what do I mean by conjugate surds? They'll be of the form a plus root b and a minus root b. So these are conjugate surds. So the nature of the roots depends on the sign and the value of d as such. So these are the basic properties that you should remember for quadratic equations. The sign of the roots also depends on, you can also identify the sign of the roots from the values of a, b and c. If the sum of the roots is positive, sum of roots, that is minus b by a, is positive, product is positive, that is c by a is also positive, that means both roots are positive. This is in case the roots are actually real. If the sum is negative, product is positive, that means that both are negative. Both roots will be negative, then the product will be positive but the sum will be negative. If the sum is positive and the product is negative, then one of the roots is negative but and another root is positive, and the positive root is absolute value of that positive root is greater than the absolute value of the negative root. If the sum is negative and the product is positive, product is negative, again one of the roots is negative, the other root is positive, and the absolute value of the negative root is greater than the absolute value of the positive root. So these are all the properties that you can see based on the determinant and on the what properties of the roots based on the determinants and the coefficients of the equation. Now a question that often comes is find the min or max value of a given quadratic equation. So how do you find that? Let me just first describe how to graph a quadratic equation. I'll just remove this for like some space. So what is a graph of a quadratic equation? So if you have a quadratic equation ax square plus bx plus c equal to 0, no, not equal to 0, this is f of x, okay. If this is your equation, then if a is positive, then your the graph of your equation is like this. If a is negative, then it's like equation where the mouth is open downwards. What does this mean? This means that it doesn't have a minima, it extends to infinity at the bottom, and but it will have a maxima as such. On the other hand, if a is positive, then you have the inversion of this, then you have like something like this. So this will stretch to infinity on the positive side, so it will have no maximum, it will just have a minima. So to find out the minima and the maxima, you have to calculate the value of minima and maxima. You can basically use differentiation. If you use differentiation, you can just, if you differentiate this equation f of x is equal to ax square plus bx plus c, you get f dash of x is equal to 2ax plus b, and f double dash of x is equal to 2a. So if you can see that the maxima or minima occurs when f dash of x is equal to 0. So 2ax plus b is equal to 0, or x is equal to minus b by 2a. So the maxima or minima will occur when x is equal to minus b by 2a. When a is greater than 0, it will be a minima. When a is less than 0, it will be a maxima. Now so this is when the maxima and minima will occur. To calculate the value of maxima and minima, you just first calculate what this value is, plug it into f of x, and then you will get what is the maximum and minimum value. In case you are not comfortable with differentiation, you can change this equation in such a way that you express this as a perfect square plus a constant value. Once you have that, then you can find out where it will occur, where the minima will occur. So for example, ax square plus bx plus c, you can say that is a into x square plus b by ax plus c. Now I can represent this as a perfect square of the form ax plus x square plus b by ax plus b square by 4a as such, 4a square. This would be a perfect square of the form x plus b by 2a as such. X plus b by 2a's perfect square would be this. So I'll express this as a perfect square in this way. Now since I've added a constant inside, I'll have to remove the constant over here. So I'll have to say c minus b square by 4a. This is equal to f of x. This is equal to f of x. So I can write f of x as I need space. I'll just clear up some space over here. So I can write f of x as so this is essentially a times x minus b by 2a the whole square plus 4ac minus b square by 4a. So the minima will occur when clearly when this part becomes 0, because this is a perfect square, and if x is a real number, then the minimum value of this function will occur when this part becomes 0, because the minimum value of a perfect square is 0, otherwise it will always be non-negative. So the minimum value will occur when x is equal to minus, this should be x plus b by 2a. So the minimum value will occur when x is equal to minus b by 2a, and the minimum value will be equal to 4ac minus b square by 4a. That is when this value becomes 0. So that is the basic fundamental behind quadratic equations. Now that you know the basic areas that will be asked, let's move on to progressions. Now progressions is an important part of this. You can expect 2 to 3 questions. So we'll try to first revise the formulas and take a look at even series questions as such. So the basic thing in progressions is that the 2 basic progressions that are asked are AP and GP. The thing that is asked is what is the nth term, what is the nth term, and what is the sum of the series, sum of terms. So an AP is essentially a progression in which the consecutive terms have a common difference between them. It's generally written as a plus d, a plus 2d, and so on. Here the common difference is d, the first term is a. So to find the nth term, we can say that if this is the first term, this is the second term, this is the third term and all. So the nth term will be equal to a plus n minus 1 times d. This will be the nth term. Now if you have to find sum to n terms, then sum to n terms will be equal to n by 2 times 2a plus n minus 1 times d. So you should remember these basic concepts as far as AP is concerned. This is extremely important to remember this. Also one thing that you should remember is that we are given that if you are given that 3 numbers are in an AP, then instead of taking them as a plus d and a plus 2d, what you should do is you should take them as a minus d, a, and a plus d. That way when you add them up together, the common difference is cancelled, and then you just get 3a as the sum. Similarly, if you have 5 numbers in an AP, then you take it as a minus 2d, a minus d, a, and a plus d and a plus 2d. So our effort here is basically to cancel off the common term. So this is the basic tricks that we used for basics of AP and GP. A GP is a progression in which consecutive terms have a common factor between them. So for example 2, 4, 8, 16, etc. So here 16 by 8 is 2, 8 by 4 is 2, 4 by 2 is 2. So this is a geometric progression. It's generally written in the form AR square, AR cube, and so on. So to find the nth term, we can say that the nth term is a raised to Rn raised to n minus 1. So this is the nth term of a GP where a is the first term and R is the common ratio. Now the sum to n terms is found out by saying a raised to R raised to n minus 1 divided by R minus 1. This is the sum of n terms of a geometric progression. Now sometimes the geometric progressions that we are given, R is less than 1. In case R is less than 1, then the geometric progression is essentially decreasing in value over time, such that after some time it will become infinitesimally small, and when it tends to infinity, the value tends to 0 essentially. So for example, consider the arithmetic progression half, 1/4, 1 by 8, 1 by 16, and so on. Here the common ratio is half. Each next value is obtained by multiplying the previous value by half. So in this case, when the geometric progression is essentially tending to 0, you can find the sum to infinity. So the sum to infinity in this case would be a upon 1 minus r. In this case, you have to make sure that r is less than 1. So this will be equal to, in this case, suppose this is half into 1 minus half. There is first term divided by 1 minus the common ratio. So this value is equal to 1. So the sum of half plus 1 by 4 plus 1 by 8 plus 1 by 16 and all till infinity is equal to 1. So these are the basic concepts of AP and GP. This is something that you need to remember to solve questions in the actual CAT. The third progression that is good to know but is almost never asked is harmonic progression. So harmonic progression is a progression in which terms of the progression are essentially inverse of an arithmetic progression. So essentially they are of the form 1 by a, 1 plus a plus d, and 1 by plus a plus 2d, and so on. So essentially the inverse of the elements of harmonic progression are in an arithmetic progression. Since there are no easy way, the nth term will be 1 upon a plus n minus 1d, but there is no easy way to calculate the sum of the terms or anything of that sort. So there's not a whole lot of point on dwelling on harmonic progression as such. So essentially, whenever you have to calculate anything for like this nth term of it, convert it into a geometric progression and then find the nth term for convert it into an arithmetic progression, find the nth term of arithmetic progression. 1 by that is the harmonic progression. So this is the basics of AP, GP and HP. Now let's move on to the concept of series. So essentially what you will be given is you will be given a series of this form and you will be asked to find the sum of the series. So the general series that comes is an AGP, and AGP is a progression in which the numerator is an AP and the denominator is in a GP. So for example 3 by 4, then 5 by 8, then plus next would be 7 by 16 and 9 by 32 and so on. So you can see 3, 5, 7, 9 etc. are in arithmetic progression, and the denominators 4, 8, 16, 32 are in a geometric progression of ratio 2. So if you are supposed to find a sum of a AGP, the trick is basically this. You have 3 by 4, 5 by 8, just take it like this. And then you have to basically shift this term 1 to the right by dividing it by 2. So if I take essentially not divide by 2, divide by the common ratio of the denominator. The denominator is in a GP, so divide by the common ratio to get to essentially shift this term to this side. So in this case the common ratio is 2, so I'll divide by 2. So S by 2 is this. So S by 2 will be 3 by 8. I put it down over here because this is what this is the column I want to actually attack by doing that. Then I have 5 by 16. Then I have 7 by 32 and so on. So if I do S minus S by 2, what do I get? S minus S by 2, I get S by 2 is equal to this minus this is equal to 3 by 4 plus 5 by 8 minus 3 by 8 would be 2 by 8 plus 7 by 16 minus 5 by 16 would be 2 by 16 and so on. So 2 by 32 and so on. So essentially what I have gotten is, I have gotten a 2 times 1 by 8 plus 1 by 16 plus 1 by 32 and so on. So now I have gotten a clean GP on my right hand side. So I can use now a GP formula to calculate what is the sum of the series. So essentially whenever you have an AGP, divided by the common ratio of the denominator, shift the terms like this, find the difference so that you get a clean GP in your right hand side. So that should be your way to tackle AGP, sum of series, when there is an AGP given. The second sum of series that generally comes is where you have a product of numbers in the denominators. So that is 1 into 3 into 5 plus 1 into 5 into 7 plus 1 into 7 into 9 plus 1 into 9 into 11 and so on. Here your basic task should be to express this as a difference of fractions. So 1 into 3 by 5 I can represent as half into 1 by 3 minus 1 by 5, because this is 5 minus 3 divided by 3 into 5. So this will be 2 in the numerator into 3 into 5, 2 will cancel and I will get again 1 by 3 into 5. So similarly I can write this as half into 1 by 5 minus 1 by 7 and so on. So what you can see is that this 1 by 5 will cancel this 1 by 5, this 1 by 7 will cancel another 1 by 7 here. So ultimately I will be like left with, like, suppose the last term of this is like 1 by 41 into 43, ultimately I will be left with just this last term. So I will be left with something like half into 1 by 3 minus 1 by 43, and then this I can easily calculate and get the value of the sum of the series. So these are the two types of sum of series that come. One is an AGP and one is a series where there is a multiplication of factors in the denominator. So basically whenever you have a sum of series, your goal should be to convert the sum of series either into a simple addition, sum of terms, or to convert it into a where a subpart is a GP or a subpart is an AP, then calculate the value for that AP or GP and then you can calculate the sum of the series. So this is how you handle series questions. Then let's go on to the AMGM inequality. So an arithmetic mean is basically, suppose you have terms A1, A2, A3 and A4 until AN. So the arithmetic mean of these terms is basically sum of these terms divided by the number of terms. The geometric mean of these terms is basically the product of these terms. So A1 into A2 into A3 to an and nth root of them, and the harmonic mean of these terms is basically n divided by 1 upon a1 plus 1 by a2 plus 1 by a3 so on till 1 by an. So essentially mostly we will be dealing with am and gm. So the thing is that these need not be in any kind of progression, these are just n terms. So the am, gm, hm property says that am is greater than or equal to gm is greater than or equal to hm. So where is this useful? So the most part that we use is this am is greater than or equal to gm part. So what you will be given is that say suppose 4x plus 9y is equal to 15, and then you are asked what is the max value of x raised to 4 into y raised to 5. So essentially now you have to find what is the maximum value of x raised to 4 into y raised to 5, and you are just given this. So what you have to do is now you have to split up x in such a way that you can you will have four parts of 4 terms containing x, and you will have 5 terms containing y. So this I will convert into 4 terms containing x, so there will be x, x, x and x, and this I have to convert into 5 terms containing y, so that is 9 by 5y, 9 by 5y, 9 by 5y and 9 by 5y and 9 by 5y. So why am I doing this? Because I can then say am will be greater than or equal to gm. So what does am will be greater than or equal to gm means? That I know that for in this case what is the arithmetic mean, if these are the values, what is the arithmetic mean of these values? The arithmetic mean will be the sum of these terms divided by the number of terms. So there are 9 terms, so the sum of the terms is 4x plus 9y, and the number of terms is 9 terms. So the arithmetic mean of these terms is 4x plus 9y by 9, so that is 15 by 9, that is 5 by 3. This is the arithmetic mean. Now what would be the geometric mean of these terms? The geometric mean of these terms will be the product of these values. So that is x raised to 4 into 9 raised to 5 divided by 5 raised to 5 into y raised to 5. So this is this raised to this square root of this 9th square root of this will be the geometric mean. Now the geometric mean is less than or equal to the arithmetic mean. So I can say that 9th square root of x raised to 4 into 9 raised to 5 divided by 5 raised to 5 into y raised to 5 is less than or equal to 5 by 3. Now I can use this equation to remove all the constant values to the right hand side, and I will get a value for x raised to 4 y raised to 5 is less than or equal to some value. So this is the basic use for finding out using this arithmetic mean and geometric mean property. So whenever you have an expression where you're given like either the sum of values and you have to find the max value for the product of values, or you are given the product of values and you have to find the minimum value for a sum of values, you use the AM-GM property to find like the max value or the min value. So in this case I would find the max value for x raised to 4 into y raised to 5 using this particular inequality. And when does you have the inequality as am is greater than or equal to gm, and when does equality occur? Am will be equal to gm will be equal to hm when all the 4 terms are equal to each other. So in this case whatever the max value is, that max value will occur when x is equal to 9y by 4 or y is equal to 5 by 9x. So once you put that value, you will get some value for x and y. So this is when the max value of x raised to 4 into y raised to 5 will occur. So this is the basic use for the AM, GM, HM property. So now that you know this, let's move on to the concept of logarithms. There are some basic formulas that you need to remember for logarithms. The questions that generally come from logarithms are basically that you have to simplify a log equation and find out the value. Only thing that you really need in that is to remember these problems, remember these formulas. So please put in the effort to actually remember them. I'll try to link them to each other as much as possible so that even if you remember just a small subset of this, you should be able to still figure out the remaining parts. That is always my endeavor as such when it comes to whenever I give a list of formulae. But given that this is just a question of practicing and just remembering formulas, please put in the effort to learn these formulas and practice so that you'll be assured like 1 to 2 questions in CAT, and that's a big deal. So please put in the effort. So the basic formula that you have to remember is that logs are defined for positive numbers. They are not defined for negative numbers. So the log value of 1 is 0 because any n number, any positive number raised to 0 is 1. So log of 1 for any base is 0. Log of any number to the same base is 1 because n raised to 1 will be 1 n. So the log of this is 1. So essentially what am I doing by log? So the funda behind log is when people did not have calculators, it was very difficult for them to do multiplications across a lot of this. So to ease the pain of multiplication and division, they found a way of converting multiplication into addition and division into subtraction. So when you have, when you say a into b, you first say log a into b, and if I say log a into b, I can write this as log of a plus log of b. Then I can look up a log table, find the log value of a, find the log value of b. I have some value here, I add that to some value here, I find some combined log value. Then I look up the reverse log table and then find what is the value for a into b. So this was the thinking behind making logarithms. They are converting a normal product kind of question into a sum addition question. So that is the thinking. So the very fundamental property of log is log of a into b is log a plus log b. Similarly, in this case, as a into b is log a plus log b, a by b, you first say log of a by b, then you convert this as log a minus log b, find the difference, then look up the reverse log and find the value of a divided by b. This was just done to ease the pain of calculation. So these are the 4 basic properties for logs as such. Now this is what some people find it difficult to understand what is going on in log. So a log is basically an exponential scale. So when you say log of a to the base b is x, what I am saying is that b raised to x is a. So for example, if I am saying that what is the value of 100 raised log 100 to the base 10, this will be 2 because 10 raised to 2 is 100. So that is my funda behind log. I am converting something like a large number into I am using an exponential scale to scale it down. So 100 is now converted to 2, 1000 will be converted to 3, 10,000 will be converted to 4. So I am just using an exponential scale to reduce the order or magnitude of this as such. So people have a difficulty in kind of wrapping their head around logarithm because it's kind of not natural. 10,000 is 10 times 1000, but on a logarithm scale it's just 1 away. So kind of make sure that you do not confuse this with your natural or like do not use things that seem intuitive to you, because the logarithmic scale is mostly not intuitive to most people. So remember these formulas, practice, that is the only way you will get comfortable and you will do solve questions correctly. So as I said, these are the 4 basic properties that are essentially definitive of like a defined log as such. Now we will come to the other property, that is log of a raised to the base b is 1 by this. So essentially the way log is defined is the property that you need to remember is this, okay, log of x to the base y. So what you can say is that this is log of x to the base z divided by log of y to the base z. So essentially if you are not comfortable with this base, you can convert this log to a base that you are comfortable with, like say log to the base 10 and this log to the base 10, and if you have ready values for this. So for example, if you have log of 32 to the base 3, now you might not have these values at hand, but you would have say the log to the base 10 table, then you can say this is log of 32 to the base 10 divided by log of 3 to the base 10. Then you can calculate these values, this divided by this will give you the required log value as such. Now this is, if you remember this is just an extension of this, because you can write this as log of a to the base b is essentially log of, sorry, I just clear up slightly over here. So I can write this as log of a to the base a divided by log of b to the base a, because I am taking a as the common base. Log of a to the base a is just 1. So this becomes 1 divided by log of b to the base a. So if you remember this, you can infer this. Now if you have, how do you infer this? So if you remember this fact that log of a into b is log of a plus log of b, You can write log of x raised to n as log to the base y of x. This I can write as log of x plus log to the base y of x, this n times, because this is essentially a product inside, right? X raised to n is essentially x into x into x n times. So I can write this as a sum of n terms. So this is essentially n log of x to the base y. So this is from this value I can just infer this value. Similarly, from the if I have x y, if the base is raised to n, then I can say that I'll convert it to y first, and by using that I'll then calculate. As I said, this I can write this as this value I can write this as, I'll first convert both sides into log to the base y. So this is log x to the base y and log of y raised to n to the base y. So this is y raised to n to the base y. I can take n outside according to the previous this. So this is n log y to the base y. So this is just 1. So this is just essentially 1 by n times log of x to the base y. So I can infer this if I know this and I know this theorem. So these are essentially interconnected. Now this comes, this a log of b to the base a is equal to b just comes from this definition. So if I have a log of b to the base a, now if I take log on, say suppose this is x, okay, now I take log on both sides. If I take log of a on both sides, what I get is I have log of b to the base a, log to the base a of a is equal to log of x to the base a. So this is 1 essentially. So I have log of x to the base a is equal to log of b to the base a. So b must be equal to a. So this is the b must be equal to x. So essentially a raised to log of b to the base a is essentially equal to b. Similarly, you can calculate the next one, where instead of let me clear up some area. So if the same way as I had done that, if you say that a raised to log of b to the base c is x, I take log to the base c on both sides. So I say log b to the base c, log of a to the base c is equal to log of x to the base c. So now I have gotten this side, log of x to the base c is equal to log of b to the base c and log of a to the base c. Now if this had been the other way around, where I had b, as I had said, if it was b of b to the log b raised to log of a to the base c, and if I had taken log to the base c of that also, again I would have gotten the same term in my LHS. So essentially I can say that whether it is log of b to the base c into log of a to the base c or the vice versa, it doesn't matter. So by reordering I can just say that I can take this into the numerator and then this into the index, and I can have the same, this is equal to b raised to log of a to the base c. So if you have this basic funda that these two rules are derived from the fact or from the definition of how log is defined, then you can infer both of these. So these are the basic rules for log. Make sure that you either are comfortable deriving one from the other and then you put in some practice to solve questions, or put in some time to actually remember these. These are important to remember, and this will give you 1 to 2 questions in CAT, so they are important to remember. Now let's go on to the next part of this, which is surds and indices. So index is basically the power to which something is raised. So when you have x raised to n, n is the index. When you have x raised to minus n, it's just basically 1 by x raised to n. When you have x raised to a into x raised to b, you can add the indices together, so you get x raised to a plus b. When you have x raised to a divided by x raised to b, you can subtract the indices, so you have x raised to a minus b. So this is the basic fundamentals or fundamental properties of indices as such. Suppose you have x y raised to n, then you can write this as x raised to n into y raised to n. Similarly, if you have x by y raised to n, you can write this as x raised to n divided by y raised to n. So these are the simple basic properties of indices. Now let's come to surds. So what are surds? So surds, as I said, mentioned in like quadratic equations. Surd is a number which has a rational part and an irrational part. So it's represented like this. Like for example, 2 plus square root of 3 or 5 plus cube root of 7. So this is the rational part. This is the irrational part. So a surd is of this form. So conjugate surds are essentially, if this is one surd, the conjugate of this would be 2 minus root of 3. So whenever you have surd, whenever one of the surds is a root of a quadratic equation, the conjugate will also be a root of the quadratic equation. So this is the basic concept behind surds. The other thing that you need to remember about surds is that rationalization of surds. So you use rationalization of surds so that if you have a surd in the denominator, it's kind of difficult to use, especially if you have like a series as such. So it makes sense to like shift the surd into the numerator by multiplying and dividing by the complex conjugate as by the conjugate surd. So what do I mean by this? So if you have say the surd in the denominator in this way, so I divide and multiply and divide numerator and denominator by its conjugate. So I multiply and divide by this number essentially. If I multiply and divide by the same number, it does not affect the number as such. So I'll essentially get 2 minus root 3 divided by, now this is essentially squared. A plus b into a minus b is a square minus b square. So essentially I get 4 minus 3. So this becomes 2 minus root 3 by 1. So essentially it is 2 minus root 3. So this is the whole funda of rationalization of surds. If you have a surd in the denominator, it might be difficult for you to actually add different surds like that together or something like that. So you rationalize the surd by multiplying the numerator and denominator by its conjugate. So this is called rationalization of surds. So these are the basic concepts you should know in surds and indices. Now let's go on to PNC and probability. This is kind of a bigger topic and it requires attention. Some of you might not be comfortable with it. I'm not going to be covering a lot of details here. If I would urge you that given the importance of this topic, please make sure that you are putting in enough effort in actually revising the topic as such. Here I'll be just covering what are the different concepts and the formulas involved. So the basic first thing that we do is what is permutation? Permutation is and what is combination? Whenever you are like say selecting things, selecting R out of n things, this is written as NCR. This is called a combination. So when you are selecting R out of n things, you are just picking things without arranging them. For example, if I have to pick, if I have 5 chocolates and I have to pick 2 out of them, it doesn't matter if I get like A and B, or so if I get like say there are A, B, C, D and E, it doesn't matter if I get A, B or I get B, A, because essentially I end up with 2 chocolates. The order of the chocolates is not important. When the order of the chocolates is not important, you are basically selecting things, and when you are selecting things, it's called combination. The formula for combination is n factorial, NCR is equal to n factorial divided by R factorial into n minus R factorial. When you are selecting and arranging things, selecting R out of n things and arranging them, then you have permutation. So permutation is NPR. This is equal to n factorial divided by n minus R factorial. Here essentially you are multiplying this NCR into R factorial. So when you are just arranging R things amongst themselves, you are going to suppose I am like A, B, C, D, E, okay. I have this and I am giving it, I am picking this and I am giving the first to person A, person 1, and I am giving the second chocolate to person 2. Now it matters in what order I pick, because if I pick A, B, it means that A goes to person 1 and B goes to person 2. If I pick B, A, then B goes to person 1 and A goes to person 2. Now the order of arrangement matters. When the order of arrangement matters, this is called permutation, and when permutation is there, then you have to also arrange the results. R things can be arranged themselves, R things can be arranged among themselves. in r factorial ways. So once you have this fact that r things can be arranged among themselves in r factorial ways, if you have to select, you have NCR. When you have to select and arrange, it is essentially NCR into r factorial, and that is how you get NPR. So that is the basic fundamental of selection and arrangement in permutations and combinations. Now the second thing that you have to remember is that when you are when you have two events, that is A and B. If A can be done in m ways and B can be done in n ways, and if A and B are independent of each other, then the total number of ways in which these two things can be done is m into n ways. So for example, if I have to pick 2 chocolates out of these 5 chocolates, and I have to pick 2 chocolates out of say F, G, H, I, J. So I have to pick 2 chocolates out of this and 2 chocolates out of this. I can pick 2 chocolates out of this in 5C 2 ways, and I can pick 2 chocolates out of this into 5C 2 ways. Since me picking out 2 chocolates out of this does not affect the result of this, me picking 2 chocolates out of this section, these two are independent events. So I can just multiply when there are 2 independent events. The total number of ways I get is by multiplying this into this, and I get the total number of ways. So I get 5C2 into 5C2. So 5C2 is basically 5 factorial divided by 3 factorial into 2 factorial. That is 4 into 5 divided by 2. So that is 10. 10 into 10, this is 100 ways. So this is the basic fundamental behind arrangement and selection as such. So if you have 2 events, so whenever you are supposed to do a series of things, first figure out whether they are independent of each other. If they are independent of each other, you count the ways for first thing, you count the ways for second thing, you multiply them together and you get the total number of ways. Now suppose you have different scenarios, that is there is scenario A, or there is scenario B, or there is scenario C. That is either suppose the condition is that these are the 5 chocolates that I have, and I should either select A or E, and I can select any one of the other chocolates B, C or D. Now if I select A, then I have 3 choices, 3 cases, that the 3 choices are B, C or D, and if I select E, I have 3 choices. And A and E together describe the total possible events that are there. So in such cases, when this is either A or E, then I have to add them together. When I have 2 exclusive events, mutually exclusive events, I have to add them up together to get the collective combined number of events. So the total number of ways would be 3 plus 3, that is 6. Essentially, whenever you have to calculate the total number of ways something can be done, then you have to write down how it is to be done. So if I write down that first I have to do this and then I have to do this, and the result of A doesn't affect result of B, then I have to multiply the number of ways of A into number of ways of B. Now instead if I write, the result can be either A or B or C, and these are the only 3 results possible. When I say these are only 3 results possible, that means that these are the collectively exhaustive events, that together they describe the all possible results that happen. Now if these are the only 3 results that are possible, then A can happen in this many ways, B can happen in these many ways, C can happen in this many ways, then A plus B plus C is the number of ways, total number of ways as such. So that is how you should define, how you should count the number of ways something can be done. So this is the basic things in which permutations and combinations is defined. Now one thing that we have assumed here is that these are distinct things. So here, for example, when I assume that R things can be arranged themselves in R factorial ways, I assume all R of those things were distinct things. Now suppose they are not distinct. Suppose P of them are of one kind, Q of them are of one kind, R of them are of, N of them are of one kind. So if say there are N items and you have to arrange N items among themselves such that P are of one kind, Q are of one kind, R of one kind, then the formula is N factorial divided by P factorial into Q factorial into R factorial. So suppose if I had 5 chocolates such that I have 2 A's and 3 B's, then the total number of arranging these chocolates is essentially 5 factorial divided by 2 are of one kind, so 2 factorial, and 3 are of one kind, so 3 factorial. So this would be the total number of ways of arranging these 5 chocolates as such. So this is the case of arrangement with repetition. So whenever you have repetition, you have to basically divide by the factorial of the number of times the item is repeated. And this is for each repetition. So if there is A is repeated n times, then I divide it by n factorial ways. If B is repeated m times, I have to divide by m factorial. So this is how you should do this. So these are the basic fundamentals of permutations and combinations. Now let us go on to a concept that is often asked in PNC, that is partitioning. So what you usually see is that there are, like, say suppose you have n distinct items into R groups. So what do I mean by distinct item and what do I mean by repeated item? For example, if you have the number, if you have, like, say balls, all are red color balls, and each ball is indistinguishable from the other, then all red balls will be identical items. Now if you have ball of one color each, so if you have n balls of n different colors, then each of them would be distinguishable from each other. So in that case, each of the items would be a distinct item. Now suppose there are n distinct items and you have to split them into R groups. Like, for example, the easiest way you can think of this is that suppose you had 3 rings. One is a diamond ring, you have a emerald ring, and you have a ruby ring. Now these 3 rings, and you have 5 fingers, and you can wear in any 5 fingers and any number of rings in these 5 fingers. So if I take the diamond ring, I can put them in 5 places. So I have 5 choices. I take the emerald ring, again I have 5 spots available, so I can put them in 5 ways. I have the ruby ring, again put it in 5 spots, so I have 5 ways. So essentially this is 5 cube. So essentially what is the, if you have R groups, in this case my fingers represent the groups and the rings represent the distinct items. When you are splitting n distinct items into R groups, this can be done in R raised to n ways. Now suppose you have identical items. So n identical items in R groups. So the way you should think of this is in terms of zeros and ones. So suppose the identical items are these zeros. So I have n zeros and I have to split them up into R groups. So I think of this that I have R minus 1 ones. So these are my R minus 1 ones. So I have n zeros and R ones. Now I essentially have to arrange them. If I arrange them, I will get some combination of ones and zeros. So what happens, what does each of these represent? So suppose in this case n is equal to 7 and R is equal to 4. So I have 3 ones and I have 7 zeros. So this particular distribution means that the first group got 1, the second group got 3, this third group got 3 and the fourth group got 0. So this is one distribution. Another distribution, say 1 0 0 1 0 0 0 0 0 1 1. Now this is another distribution. This is another, there's 3 1. So this is another distribution. This means that the first guy got 0, first group got 0, the second group got 3, the third group got 4 and the last group also got 0. So depending on my distribution of ones and zeros defines a unique distribution of the identical items in the R groups. So these are essentially I have to arrange n zeros and I have to arrange R minus 1 ones. So how many ways can I arrange this? So if I have n zeros and R minus 1 ones, the number of ways of arranging them would be n plus R minus 1 factorial. But I have repetition, so I have to divide it by n factorial and R minus 1 factorial. Now this is essentially a combination formula, because if you know NCR is essentially n factorial divided by n minus R factorial divided by R factorial. So this formula can be written as n plus R minus 1 C R minus 1. So I get this value as n plus R minus 1 C R minus 1. So this is the basic fundamental of how I can divide n identical items into R groups. Now suppose I have an additional condition that I have to, when I am dividing the n identical items into R groups, I have to make sure that each item is, each group gets at least one this. That is, this case of this person getting 0, this person getting 0 does not occur. If I have to make sure that each person gets at least one item, what I do is I start off by first giving off these R this. So firstly I put all, in all groups I put one item. Now once I have removed R balls, R items, I am left with n minus 1 items. n minus r items in which I can put in r groups indiscriminately. I now need not follow n condition. Now this I can do in n minus r plus r minus 1 c r minus 1 ways. So this is essentially n minus 1 c r minus 1 ways. This is when I need to put at least one item in each of the groups. So this is the basic fundamental of division of partitioning of identical items into different groups. The same fundamental can be used for number of integral solutions. So suppose you have an equation like this, a plus b plus c plus d is equal to 9. Now how do I find the number of integral solutions for this? Now I can assume that a is 0, b is 0, c is 0 and d is 9. Or I can assume a is 0, b is 0, c is 1, d is 8 and that is one integral solution. But this is essentially the same as having n items, so n ones. I have n ones and I have to distribute them across 4 groups. The groups are a, b, c, d. So I have to then follow the same concept of where I have to find out how many ways I can distribute this 9 across 4 groups, and I have to follow the same this and I have to use the same formula. So this is the basic concept of even finding the number of integral solutions. When you have to find the number of integral solutions, you can use the same formula to find the total number of integral solutions possible that satisfy a particular equation. So this is the fundamental behind partitioning. The concept of derangement is a short one, but it sometimes is useful. For example, in last CAT, the concept of derangement came in a LR set. So I'll cover it because it's a very short and simple this, and if it comes then there's nothing like it. So what is a derangement concept? So derangement basically means, it stands for disarrangement. That means that suppose there are 3 envelopes, say E1, E2, E3, and 3 letters L1, L2 and L3, and this L1 is destined for this was supposed to be given put in envelope 1, L2 was supposed to be put in E2 and L3 was supposed to be put in E3, but they got disarranged in such a way that none of the letters ended up in their intended envelope. This means that there is perfect disarrangement. See, perfect arrangement is L1 into E1, L2 into E2, L3 into E3. Now a random arrangement would be some go into their intended envelopes and some go into other envelopes. A perfect disarrangement is none of them go into their intended places as such. So the derangement of n means that none of these n items go into their intended places. The formula for derangement of n, so derangement of n is written like this, where the apostrophe is put before n. So this is equal to n factorial into 1 plus 1 by 1 factorial, 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial and so on till you have minus 1 raised to n by n factorial. So instead of remembering this, just remember some basic values for this. If you have n is equal to 1, you cannot disarrange 1. If you have n is equal to 2, then there is just one way of disarranging. If you have n equal to 3, then the number of ways of disarranging are 2. If you have n is equal to 4, then this is 9, and when n is equal to 5, the number of ways of disarranging is 44. So if you remember these, generally you will have derangement questions for up to 4 only. So if you remember these 5 values, it's pretty quick for you to solve questions based on disarrangement. So this is the concept of derangement. Let's move on to the concept of probability. So probability, answering questions of probability correctly depends entirely on whether or not you understand PNC properly. Because most of the cases you have to calculate the number of ways, and once you have calculated the number of ways, you have to divide it by the total number of ways. So essentially probability of an event occurring is essentially defined as number of favorable outcomes divided by total number of outcomes. So for example, if you have a deck of cards and you have to select 2 cards out of it. So how many ways can you select 2 cards out of it? You have 52 cards, so you can select 2 cards out of it in 52 C2 ways. In how many ways can you select 2 kings out of the 52 cards? So there are 4 kings, so you can select it in 4 C2 ways. So what is the probability of the event that you pick 2 cards out of a deck of cards and both of them are kings? The number of probability of that event is the probability number of favorable outcomes, that is 4C2 divided by 52C2. So this is the basic concept behind probability. Now for answering this question correctly, you needed to know how to calculate the number of ways of picking 2 kings out of a deck of cards divided by the number of ways of picking 2 cards at random out of a deck of cards. So this is how probability is defined. Another definition that is there is odds in favor. So odds in favor is basically essentially number of favorable outcomes by number of unfavorable outcomes. Odds against is essentially the inverse of that, that is number of unfavorable outcomes divided by number of favorable outcomes. That is the basic concept of odds in favor and odds against. Another important concept that you need to remember in case of this is that if you have essentially set theory, kind of this, where I said that you have to pick 2 kings, but it can be that you have to pick, the event can be you have to pick 2 kings or 2 hearts. Now these are 2 events. First is probability of say A is picking 2 kings, B is picking 2 hearts. Now these are not disjoint events. You can pick 2 kings and 2 hearts, or you can pick a king with a king of hearts also. So these are not 2 disjoint events. You have to consider P of A, P of B, and also P of A intersection B. So so if the question is what is the probability that when you pick 2 cards from a deck of cards, that you pick either 2 kings or 2 hearts. So in this case I will have to find P of A union B. So P of A union B is P of A plus P of B minus P of A intersection B. So what is P of A in this case? Probability of picking 2 kings is 4C2 by 52C2. Picking of 2 hearts, there are 13 hearts, so 13C2 divided by 52C2. Now the way I have to remove the case where I have one of the these cards that I pick is one of them is a king of hearts. So the case where I will pick one card as a king of hearts, essentially I can't have 2 kings and both are hearts. But I can have the case where actually there is no A intersection B, because I have either it is 2 kings or 2 hearts, then A intersection B is 0. So I'll actually take a different case where, say, suppose it is 1 king or a heart. So 1 king or 1 hearts. So 1 king I can pick in 4C1 base and 52C1. 1 heart I can pick in 13C1 base, and total number of cases is 52C1. Now the way I can pick both a king and a heart is one way. I pick the king of hearts. So that is minus 1 divided by 52C1. So this is the total number of cases. So I have 4 plus 13 minus 1. So I have 17 minus 1. So I have 16 divided by 52. So this is the total number of ways I can pick either a king or a card of hearts. So this is basically the formula that you should remember. P of A union B is P of A plus P of B minus P of A intersection B. Now the second formula that that you should know is that of conditional probability. As I had said, there is also this of independent events. So the basic fund of independent events is number of ways of doing A and B. If A and B are independent of each other, is number of A into number of B. Now this translates into probability also. So probability of A intersection B, if A and B are independent events, is P of A into P of B. So this is a basic concept when you have probability of 2 independent events. For example, in the earlier case I had considered the probability picking 2 chocolates from one set of 5 chocolates and 2 chocolates from another set of 5 chocolates. Then what would have been, like, if the question would have been what is the probability I chose A, B and EF. Now probability of choosing AB is 1 by 5 C2, and of choosing EF is again 1 by 5 C2. So multiply them together, I get the probability of choosing EF, AB from first and EF from other. Because these are 2 independent events, I can just multiply their probability together. So now we come to the concept of conditional probability. So conditional probability is the probability when you have additional knowledge. So most of the probability that we calculate, that is what is the probability of event occurring, that is a priori probability, where you don't have any other knowledge of some event already occurring that could have impacted this. But now suppose that you know that event B has already occurred. Now you want to calculate what is the probability of A given that event B has already occurred. To calculate that, you basically say that what is the probability of both occurring given that B has already occurred. So this is how we calculate probability of event A given B has occurred. Now suppose you don't actually know the probability of B. The way you calculate is you say A intersection B divided by P of A intersection B plus P of A dash intersection B. So if you add both of these together, you get essentially probability of B occurring. So this is the concept of conditional probability. Bayes theorem is essentially based on this, where you essentially say A of P of A given B is equal to P of A intersection B given P of B, or I can write this as also as P of this essential I can write P of A intersection B as P of A given B into P of B, and I can also write this as P of B given A into P of A. So Bayes theorem is essentially equating these two parts. So this is the fundamental behind conditional probability. In conditional probability, always see if like there is one event given, we have to calculate the probability of event, and some event has already occurred. Then you have to figure out what is the probability of A and B both occurring. Then you divide it by the probability of just B occurring, and then you get the probability of A occurring given B. So that is the basic concept of probability. Let's move on to the concept of Venn diagrams. This is a pretty simple topic, but still 1 to 2 questions come out of it, and it also has application in DILR, so it's important to revise this. The basic thing that you should remember in Venn diagrams is to understand where to put things. So for example, most of you would be okay with like 2 set Venn diagrams. So suppose this is set A, this is set B, and this is the superset. So this set is the universal set, which is a set of all elements under consideration. This is this part, like say with teal, is all the elements that are there in A. This part in yellow is all the elements that are there in B, and this part in dark blue is all the elements that are there in A intersection B. So this is A, this is B. Now if I have to say what is only A, what is only A? This part is only A. Now so I'll use this color. This part is only A, so that is only A. So only A is basically A minus A intersection B. What is only B? Only B is this part here. So only B is B minus A intersection B. So you just remove the overlap part to get the only A part, only B part. Now what is neither A nor B? Neither A nor B is this part outside over here, like say this part. So this is neither A nor B, that is not part of any of the sets as such. So for a 3 set Venn diagram, you can write it as like, instead of saying that A minus A intersection B, you can write this as you can write this as A and B dash. So that way you will not have anything that is part of A. This is only A. Similarly, only B is B and A dash. Now with 3 things, when you have, this is C dash. So you have, when you have 3 elements, only A will be A intersection B dash intersection C dash. This means it's part of A but not of B and C. When you say part of A and B but not C, you have A and B but not C. So this is how you should define that. So this is that A and B but not C. A and B and C is the center part. A but not A and C but not B is A and B dash and C. Not only C is A dash and B dash and C. Not part of A but part of B and C is A dash and B and C. Not part of B or C is A dash and B and C dash. So essentially, once you are comfortable with this, this is not part of, so A dash and B dash and C dash is the part outside this, and this is the universal set. So you should be able to read the sentence and say if it's written only A, then it's this part. If it's written only B, it's this part. If it's written only C, it's this part. If it's written that part of A but not B, then it is these 2 parts. it's written part of B but not C, then it is essentially everything which is over here, like this entire portion. So you should be able to see what is asked and accordingly understand the areas that are represented. That is the only thing that you have to understand in Venn diagrams. The other thing that you have to do in Venn diagrams is max and min of overlap. So when you have two Venn diagrams like this, and suppose you are asked what is the max overlap. So the max overlap would be the overlap when the smaller Venn diagram, smaller set is part of the bigger set. So suppose this is like 50 people and this is 30 people, and this is a set of 100 people. So the max overlap is when this 30 people are entirely in this set of 50 people. So that means this 30, this is 30, this is 0 and this is 20. What would be the min overlap? The min overlap would be then when none of them are in this to each other. Now suppose in this case where there are 100 people, this has 60, this has 80. Now in this case if there is min overlap, you can say this has 50, this has 0, this has 30 and this is 80, this is 20. So you can have a min overlap of 0, but in certain cases you can't have a min overlap of 0 because you have 60 here and you put 80 here, the total cardinal set value becomes 140 and that's impossible. So clearly there is an excess of 60 plus 80 minus 100, there is an excess of 40. So that 40 has to be accounted for by this overlap. So I'll put 40 here, then 20 here and then 40 here. So this is the min overlap in this case. Whatever is the excess value of set 1 plus set 2 minus A union B, this will be the excess value and that has to be accommodated in the overlap. So this is the min and max overlap in case of two set Venn diagrams. The max overlap in this case is when the set of 60 is entirely inside the set of 80. Now in the case of 3 set Venn diagrams, it kind of gets complicated. So instead of drawing that out, we can use simple equations. So what we do is we say this is the 3 set Venn diagram. All the elements that are part of only one set, I'll say are part of S, are part of 2 sets, exactly 2 sets are part of D, and part of exactly 3 sets are T. So this is equal to A union B union C. These are sets A, B, C, say. Now I also know that if I add A plus B plus C, I'll be counting those that are part of one set exactly once, I'll be counting those that are part of 2 sets twice and part of 3 sets thrice. This is A plus B plus C, that is number of elements of A plus number of elements of B plus number of elements of C. So if I remove, like if I take this minus this, I get an equation where I get D plus 2T is equal to some constant. This constant like shows the excess like this. Like here in this case we had this 40 as excess. This also is an excess. This excess cannot be represented by just saying, okay, you know what, we'll set all the overlap values to 0. You can't set all the overlap values to 0 because of this excess. If this value is 0, you can directly say that the min overlap is 0 because then there is no excess as such that you have to accommodate on the overlap values. So this is essentially the the excess value that you have to accommodate in the places which are like overlapping, either in exactly 2 or in exactly 3. So what would be the minimum? What would be the minimum overlap? The minimum overlap would be when much of this K is actually accommodated in T, because here we have coefficient of T as 2. So every element of T will be counted twice in the excess. So suppose our overlap is 20. If T is equal to 10, then this equation is satisfied. On the other hand, if I have to say what is the, so the min overlap would be 10. The min overlap will occur when I maximize T and minimize D. On the other hand, if I have an excess of 20 and I have to maximize the overlap, then I will try to accommodate everything in D because I am trying to maximize for each element of K, I am getting one element in D. So I am maximizing my overlap by maximizing D. So when you have 3 set Venn diagrams, to minimize the overlap, you have to minimize T, to maximize T. When you have to maximize the overlap, you have to maximize T. So this is a basic equation you have to play around in to get min and max overlaps in Venn diagrams. Now let's come to functions. Functions can be incredibly complex, but generally the functions that have come in CAT recently require you to just plug in values. So let's discuss the basic things of functions, because that would have been enough for you to solve the recent CAT questions. So what is function? A function f of x is defined in such a way that you will get an expression in x over here. So that is what f of x is. The domain of x is basically all the values of x such that f of x is real. F of x is real and defined. What is the codomain of x? Codomain of x is basically, codomain of x is essentially all the values f of x can take. And what is the range of x? Range of x is essentially all the values of f of x given the domain. Now for example, consider the case where f of x is equal to square root of 16 minus x square. Now this is the value of, this is the function f of x. Now what is the domain of x? Now f of x has to be real and defined. So for f of x has to be real, then this value inside the square root has to be positive, non-negative. For this value to be non-negative, x square has to be less than or equal to 16. That means x has to be less than or 4, or between minus 4 to 4. So this is the domain of x. What would be the codomain of x? All values f of x can take. So we see that f of x is basically positive square root value. So f of x can take all positive values as such. So that would be the codomain of x. What would be the range of f of x? Range of x would be the values that you can take given the domain. Now the domain is the fact that it is lies between minus 4 to 4. So what is the range of values that can this value can take given that x is between minus 4 to 4 is the range of x essentially. Generally codomain is not asked. What is asked is what is the domain, what is the range. So domain would be the values of x where the function is real and defined. Why is the part defined at? Because if suppose you have something like f of x is square root of 16 minus x square divided by x minus 3. In this case, f of x is not defined at x equal to 3. So x equal to 3 will not be part of domain of x. That is the basic thing. The range of x is basically all the values it can take given the domain of x. So that is what is domain and range. The second concept that you need to learn is of even and odd function. A function can be neither even or nor odd. That is the bulk of functions actually. So what is an even function? An even function is a function such that f of x is equal to f of minus x. So for example, if f of x is equal to modulus of x, or f of x is equal to x square. Now if you put even minus x here, minus of modulus of x will be equal to modulus of x. It does not affect, the sign of x does not affect the value of f of x. So these are even functions. So what is odd function? Odd function is basically f of x is equal to minus f of minus x. So for example, f of x is equal to x cube. When f of x is equal to x cube, when x is equal to minus x, this becomes minus x cube. So f of minus x is equal to minus f of x. So this is a basic function of what is a odd function and an even function. So most times what you get in function is just plug in the value and you will get this. You will have like f of x is this, g of x is this, what is f of g of x. Just plug in the values and you'll get the value for the function. It's not really difficult at all. Now let's move on to this value, this that is used often in functions, that is the modulus functions. This is the only thing that is slightly tricky. So the basic thing in modulus is whenever you are given a modulus, you have to split it up into ranges. You have to say that okay, if x is less than 0, then this is equal to minus x. When x is greater than or equal to 0, this is equal to x. And you have to remove the modulus sign by considering separate ranges and calculating what is the f of x without the modulus sign in each of those ranges. Now, so the basic thing that you have to do in modulus is basically whenever you are given a modulus function, like say f of x is equal to modulus of x plus modulus of y, you have to remove the modulus sign. So by doing that, how do you do that? You basically say that if I have to remove the modulus sign, I have to basically say that I have to define ranges. So when x is greater than 0 and y is greater than or equal to 0, this is essentially equal to x plus y. when x is greater than 0, greater than or equal to 0 and y is less than 0, this is x minus y. When x is less than 0 and y is greater than or equal to 0, this is essentially minus x plus y. When this x is less than 0, y is less than 0, this is minus x minus y. So this is how you should split up, you should remove the modulus sign, identify ranges and split up the function, define it explicitly in the different ranges. So generally what you will be asked is, you will have a function with modulus function and you will say how many x and y values in this function satisfy the given equation. Split it up into ranges, see for each range how many values satisfy the given equations. Once you get a solution, see whether that solution actually lies in the range, and if it lies in the range, then count it as a possible solution. So this is a basic funda that you need to use while solving questions involving modulus. So now that is about modulus. Let's go on to the concept of maxima and minima. So this is often used in conjunction with functions or like with quadratic equations and graphs. As I had said already, with quadratic equations you can use basic differentiation. A lot of students are not comfortable with differentiation, so I'll just cover it in brief over here because it's a very easy way to calculate maxima and minima given any function. So if your f of x is of this form where you have a raised to x raised to n plus b raised to x raised to n minus 1 and so on, when you calculate f dash of x, this is the first derivative of x by x, you get n times a raised to x raised to n minus 1 plus n minus 1 times. So you take the index out, multiply that as this into b into x raised to n minus 2 and so on. If there is a constant value, that constant value disappears. Okay, so that is a basic funda of taking derivation. And if I take a double derivation of this, this becomes, now I have to take this n minus 1 here. So this is n into n minus 1 times a into x raised to n minus 2. So you can see the general this. Now I have to take this index down here, n minus 1 times into n minus 2 times b into x raised to n minus 3 and so on. So this is the basic funda of how I calculate first derivative and second derivative. To calculate maxima or minima occurs when f dash of x is equal to 0. To check whether what it is, maxima or minima, you check whether f double dash of x is greater than or is negative or positive. So if f double dash of x is positive, then it is minima. If f double dash of x is negative, then it is maxima. So this is the basic fundamental of calculating maxima or minima of functions. Given that this is not really technical, if you just learn how to do a simple derivation, you can easily calculate maxima and minima. I would urge you to do this because otherwise finding out maxima and minima involves you to do a lot of shifting of equations and all, which is not necessary. When some easy tool is available, we should use it. So this is the basic concept of maxima or minima of functions. So we have covered all the other quant topics. So through these videos, we have tried to revise all the basic concepts that are there in quant, all the quant topics that are there. Please make sure that you attempt all the questions that are there in the classroom session. Please make sure that you see the description box for related videos. Please start practicing every single day. Now is the time to practice. Make sure that you put in a lot of effort in solving questions. So an ideal starting point would be for all the topics, quant topics that I have discussed today, try to solve 5 questions each. So that is the only way that you will actually know that have I properly revised that topic or not. So please start solving questions, please start practicing. Thank you for tuning in.